For this question, we see that the operating voltage across a X-ray tube is increased. Which of the following gives the corresponding change, if any, to the lambda 1 and lambda 2? So lambda 1, right, actually refers to the lambda minimum. Okay, so what's the origin of this lambda minimum? It's because, right, you see these electrons, they are fired, okay, towards the target matter, okay, with a accelerating voltage. So this will give them Ke. So the Ke of the electrons, right, will be equals to E times VACC. Okay, and these electrons go around the nucleus of the target atoms, okay, and losing energy. The maximum energy that they could lose, right, in one particular encounter will be all the Ke that it has brought there. Therefore, if you equate, right, the loss in Ke, you see this K is lost and turns into what? Turns into a photon, okay, gives out a photon. So Hc over lambda, yeah. And since you lose all your Ke, right, so it's just everything here. So you have a Hc over lambda minimum. Okay, so this is the origin of the lambda minimum. So when you increase the operating voltage, you cause the electrons to have more Ke to hit the target matter. Therefore, they could have lost more energy per encounter or lose everything. Therefore, the X-ray photon they give out will be more energetic, hence smaller wavelength. So lambda 1 will decrease. Okay, lambda 2 is the wavelength, right, for one of the peaks. If we look at this, right, this is likely the K alpha, but we actually don't need to know. So let's just briefly talk about the origin of all these characteristic lines. So the incoming electrons, right, is like here. Okay, this is the incident electron. I'm just drawing the energy level because I don't want to draw the actual diagram. Okay, so this electron, right, comes in, hit this guy, okay, so and it flies out. So this is the original one. This guy, right, also flew out. So this guy also flew out. So originally, right, he was there, now he wasn't. So here, right, you have a vacated state. This vacated state, right, is the envy of the other electrons in the less inner shell or the outer shells. So they will want to de-excite to occupy that vacated state, thereby giving out a photon. Okay, and that gives rise to the right, to all these characteristic lines. Yeah. So this wavelength, the wavelengths of these photons given out through this mechanism, right, is dependent on just the matter itself. Okay, because, right, different matter will have different energy level diagram. Therefore, the transitions, right, will have different delta E. Okay, hence different wavelength. Okay, so will lambda 2 change as a result of you changing the operating voltage? Not at all. Okay, so lambda 2 may change only when you change the target matter. Okay, let me just note it down. Only dependent on target matter. Just a quick note again. Why is it that characteristic lines, right, are called characteristic lines? It's because, right, depending on the positions of this line, they tell us, right, this spectrum, right, is corresponding to this matter. Another matter will have different locations for these lines. So every matter will have different set of spectra. So therefore, is special and unique. So that's why we call it characteristic lines.